Why do molecules in very distant galaxies seem to be built with a slightly different ruler than the same molecules in our labs? In the energy filament theory, a molecule is not a few balls glued together, but a small band of electrons and nuclei locking their rhythms inside an energy sea whose tension has been slowly changing across cosmic time. Textbooks treat molecular structure as something we've basically nailed. On Earth, we measure bond lengths, bond angles, vibration frequencies, rotation periods, and energy level gaps for common molecules, and we store those numbers as the standard shape and the standard rhythms. When astronomers point high-resolution telescopes at molecular clouds around remote nebulae and quasars, they expect to see the same patterns, just shifted by redshift. Instead, they keep finding that the details are slightly off in a very systematic way. The lines that reveal bond lengths point to bonds that are a bit shorter or a bit longer than our lab values. The vibration beats of the molecules are a little faster or a little slower. The overall ladder of energy levels has the right outline, but the exact line positions and relative strengths feel subtly wrong. As if the familiar ruler had every tick mark still in place, but the spacing between ticks had been gently stretched or squeezed. The first reaction is to blame local conditions and instruments. Messy gas, turbulent motion, extreme temperatures, scattering along the path, plus calibration and noise in our detectors. All of that matters and does explain part of the mismatch. The nagging part is that for the same type of molecule, seen in very different galaxies, the deviations often lean in the same direction, which is harder to dismiss as pure local coincidence. In this picture, that is exactly what you would expect. A molecule is really a compromise between several internal rhythms: fast electron motion around nuclei, slower structural modes inside the protons and neutrons, and the way outer electrons latch and share pads to create bonds. Put differently, it is a small band in which electrons provide the high notes. The nucleus provides the bass, and the three-dimensional shape sets the chord structure. Earlier episodes showed that each of those ingredients reacts to tension differently. Electron timing shifts in atomic clocks. Proton and neutron structures respond with tiny changes in size and lifetime. Internal electron flow rearranges its magnetism, and fragile pairs like positronium adjust how long they survive. None of these adjustments are perfectly synchronized, so when the same kind of molecule is assembled in a region of the universe where the energy sea is tighter or looser than it is here, the best bond length and best bond angle are recalculated by nature for that local tension. The vibration frequencies, rotation periods, and level spacings are all tuned to fit the particle rhythms of that era, not ours. You can think of each molecule as being stamped onto a piece of paper whose grain and stiffness are set by the local energy sea. Print the same design on softer paper and the lines sagging a bit. Print it on stiffer cards and they pull straighters. And if you measure very carefully, the geometry is never quite identical. In the same way, a water molecule or a carbon monoxide molecule in a distant cloud is still water or CO. But its structure carries the ruler marks of that time and place, not the ruler on your lab bench. That means strange-looking molecular sizes and slightly shifted molecular spectra are not random nuisances. They are the third layer in the same story we've been telling. Redshift is the big signal, showing that particle rhythms as a whole were slower in earlier epochs. Fine distortions inside spectral lines are the smaller signal, showing that different particles slowed by different amounts. These weird molecular rulers are the finer signals still, where the evolution of particle structure has been carved directly into molecular shape and motion, only visible when a molecule is bright enough, clean enough, and well measured enough that tiny mismatches stand out against the noise. When you see a distant molecule that seems just a little wrong-sized, you can read it as that patch of the universe using its own era's ruler, built from its own particle rhythms, to tell you about its past. In that sense, the chemistry of faraway clouds is not just about what molecules exist there. It is also a quiet archive of how the energy sees tension, and the particles living in it, have changed. Tap follow, share it on New Physics, Clear Universe.